In this video, we begin section 4.6. The title of this section is Indirect Argument, Contradiction, and Contrapositive. In this section, we are going to introduce a new technique for proving arguments. This technique is going to be called an indirect method of proof. And this method uses the contradiction and the contrapositive methods. They are very similar with some subtle differences. We start with the proofs by contradiction first, and then we talk about the proofs by contrapositive afterwards. When we're using the method of proof by contradiction, we should do the following. We start by supposing the statement to be proved to be false. So whatever question you have, whatever statement you're trying to prove, you're going to assume that it's false. In other terms, you're going to assume that the negation of the statement that you want to prove is actually true. Now, since the statement you want to prove is actually true, supposing the negation is true will lead to a contradiction. That contradiction will tell us that the original statement that we had to prove must be right because its negation is leading to a contradiction. Remember, a statement can either be true or false. So if the original statement is true, then the negation of it is false. By assuming that the negation is true and leading to a contradiction, we get to verify that the original statement is in fact true. Let's practice this by doing a couple problems. Theorem 4.6.1 says there is no greatest integer, which is obviously a true statement. So how do I go about proving this statement? Keep in mind, I want to do a proof by contradiction at this point in time. So the first change compared to what we did before is that now we are going to write at the very top of the proof by contradiction. Normally we don't write anything right there, we just write the word proof and we move on. However, to be extra clear, I want to mention that I'm doing a proof by contradiction so that the reader could mentally prepare to the following kind of proof. This is an indirect way of proving things. So in order to show that the theorem is true, I'm going to do a proof by contradiction, which means I'm going to start by writing the words suppose not. And I'm going to explain what it means to suppose not. In this case, it means that I'm going to suppose, for the sake of a contradiction, that there's a greatest integer. So notice how I wrote the words for the sake of contradiction. So in other terms, I'm telling the person that this assumption is going to lead to a contradiction, meaning it will become eventually false because it's leading to a contradiction. So its negation, which is the statement in the theorem, is going to be a true statement. Okay, so again, our goal is to show that the assumption that there is a greatest integer will lead to a contradiction, making the original assumption in the theorem true. So how can I derive my contradiction? How can I get this contradiction? Well, let's interpret what it means to say there is a greatest integer. Well, if there's a greatest integer, then let's go ahead and give it a name. In this case, I'm going to call that integer n. So n is supposed to be like the largest integer that you can ever find. But we also know that 0 is less than 1. This is pretty much basic mathematics. It doesn't have to be even proven. Everybody knows that 0 is less than 1. So we can add a positive number n to both sides. Remember, n was the largest integer, so it's obviously going to be positive. And I could add it to both sides, and this does not change the inequality direction. But 0 plus n is n, and n plus 1 is going to be a new integer. That is, according to this inequality, greater than the integer n. Well, this is a contradiction, because we had assumed that n itself was the greatest integer. So assuming that n itself is the greatest integer leads me to the conclusion that n plus 1 is an integer greater than it. And this is the complete nonsense that we're talking about. It should have been that n is the largest one, not n plus 1. So obviously, this implies that the assumption we made earlier, saying that there is a greatest integer, must be false, because it's leading to a contradiction. So this means that the theorem is actually true, and it means that there is no greatest integer.